Okay, so you had the final. Any questions? No, you had the midterm. Any questions? Did you get the solutions to the midterms? Is there any question that you would like me to explain? Well, we have already scanned your exams. Well, the main difference will be for us. I mean, now we won't be just passing your papers around to the instructors. So all of us will be able to read it simultaneously. Hopefully, we will announce the grades faster. So you see, some of them are already graded, some of them not. And to see your exam papers, you will not have to go to the office of an instructor, etc. So because in last semester, for example, if you wanted to see your exam papers, some of you probably waited for hours to see your papers. This semester, it will not be the case. So you will just go to your computer and log into this system. And once the grading is done, you will see your grade and your exam paper through this system. If you want to object to any of your gradings, we haven't yet decided. Basically, the system allows you to make your objections through the online system. That is one possibility. But it seems to be more likely that if you want to object, you will go to your section instructor and talk with him. And if you convince him, then you will write down your objection, and the lecturer grader who graded that question will regrade your answer. So it's had to... Yeah, I mean, you will have to come to me. As I said, the majority of the change is for us. Well, I always get that question. The students always ask, when will you announce the grades? I always tell them that when I grade them. But then they ask, when will it be? Well, then I say, when I grade them. So it's not easy to give a deadline. Definitely before the second midterm. So you will have a chance to see your papers before the second midterm. That I can guarantee. Other questions? About physics rather than your exam grades? Now, on Thursday, we had kind of discussed the capacitors. Okay, the capacitor, the general idea was, one simple example was the parallel plate capacitor. So when you have these two plates nearby, you can put some charge on it. If you put some charge on it, then you are basically creating a potential difference. And we said that there is the battery. The plus and the minus. So this plate becomes positively charged. This plate becomes negatively charged. If there is a charge Q, then the charge Q on the capacitor is proportional to the potential. Well, this is true independent of the shape of the capacitor. Whatever the shape is, the potential difference that you create will always be proportional to the charge on your capacitor. The capacitance will, the only shape dependence and the material dependence is in the capacitance. So the C depends on how you create this system. And C is independent of how much charge you put on the system. C is independent of Q and V. And the proportionality of Q and V is as I said, independent of the shape of the system. The C depends on the shape, whether you put a dielectric or not. It depends on all the other parameters of your system. And, well, one thing that we didn't discuss that we will begin today will be, well, how does the battery put the charge in the capacitor? So basically now we are starting to discuss currents. That is moving charges. We are no longer in the domain of electrostatics. You see, if you remember, we said that up to this point we are studying electrostatics such that in our system, in the systems that we had studied, no charge is moving. So there cannot be any moving charge. Now we are allowing the charges to move around. But of course, some of the results that we derived before, some of the conclusions we had before were based on the fact that the charge should not be moving anymore. Do you remember any such conclusion? There was at least one thing we said that this cannot be because charges are not moving. So?
The charges are not moving.
Okay, insulators are, in the insulators there are no charges moving, so that we cannot create currents in the insulators. What else?
There's no electric field.
Well, we said that inside the conductor there is no electric field. And our reasoning was that if there is an electric field inside the conductor, then that electric field will exert a force on the charges, and the conductor is defined as some material in which the charges are, some charges are free to move. So if there is an electric field inside the conductor, then that electric field will cause the charges to move, and we said that in electrostatics that cannot be. But now we are no longer in electrostatics, so that result is no longer true, which means that now we can have electric fields inside conductors. This will be one of the important distinctions between what we will be studying now and electrostatics. So just don't get confused. Before, we did say that we cannot have electric field inside conductors because we were in electrostatics. Once we are no longer in electrostatics, there is nothing that prevents electric field inside the conductor. Okay, how do we create that electric field? Let's start with that. Basically, that is what the battery will do. Now, when we have, let's say, let's take some conductor. We had already said that if you put this conductor in an electric field, well, negative charges will accumulate here, positive charges will accumulate here. So positive and these new induced positive and negative charges will create an additional electric field in the opposite direction. So eventually, when the accumulated charge is large enough, we won't have any electric field inside. But this happens only if the charges accumulate. Now, that is what the battery does. It takes charges from one side and dumps charges on the other side. Now, in a conductor, in a metal, let's say, it's usually the electrons that are moving around. So this is the flow of electrons. But the current is running in the opposite direction. Now, in a real circuit, it's the electrons that are moving, because in real circuits we use metals as our conductors. And in the metals, it is the negative charges that are moving. So it's the electrons that are actually moving. But the convention, the convention in the definition of the current is always in the sense of the motion of the, pseudo motion, let's say, of the positive charges. Now, the reason for this confusion is basically because when we first discovered currents, we didn't know about the electrons. We didn't know about the positive charges. We didn't know about the negative charges. So we just assumed that it was the positive charges that were moving around. And then when we discovered the electrons, we also discovered that the electrons is negatively charged. So the flow of the electrons is basically the opposite to the direction of the current. Now, how does a battery do that? They create a potential difference. An almost constant potential difference. So they don't actually create a constant current, but what they do is they create a constant potential difference between the two electrodes. So a typical battery that you also find at home is some solution. Salt or acid solution. It can be liquid, it can be solid, it can be various different kinds of chemicals. And inside this solution, in fact, you need to have two different kinds of metals. But the most commonly used one is on one hand you have carbon. On the other side you have the zinc. Have you ever opened an AA battery? No? How many of you opened up an AA battery? The normal batteries.
Yes. There is like something like coal.
Well, you see, if you look at that battery, it's like a long cylinder. This is the outside is the positive. This tip is the negatively charged electrode, and this electrode is actually connected to a carbon rod. Inside you have some kind of a paste. And outside is mainly zinc. This is what the typical battery is. Of course, nowadays we use many different chemicals inside, but this is essentially the basic idea. And what happens inside is, okay, the negative electrode gives out electrons, so you get the chemical reactions in which an electron is ripped from the zinc. Inside, the electrons are ripped from the zinc and they just are deposited in the carbon. And then it runs through your circuit, whatever you have in your circuit, and then it goes back to the zinc. This is the main idea. If you have probably seen videos where people just light bulbs using potatoes or lemons. Well, lemon is nothing but some acid solution, just like potato. The critical thing here is that you have to have, if you put the same metal inside the chemical, you don't get any current. You have to put different metals, or one of them can be replaced by carbon. And the current is basically created by, basically it's created by what's called the different electron affinity of different elements. You have probably studied it in chemistry. So, as I said, again, just like the battery basically transfers the chemical energy is stored inside your chemical into what we call the electric energy. And basically, the potential difference between these 2 points, this point and this point, is more or less constant, V. As we will discuss this week, it's not exactly constant if there is a current running, but more or less constant. And most of them, for these type of batteries, is 1.5 volts, somewhat around. It changes from battery type to battery type. Not all batteries are 1.5 volts. If you have rechargeable batteries, for example, they are usually around 1.3 volts. Now, it's experimentally found that if you have such a circuit, so you have your battery, you connect your battery to something. It might be a light bulb. Or it can be your radio. Or whatever you can think of. It can be your cellular phone. Your cellular phone also has its battery in it. There will be a current running through your system. Well, what we call the current is actually, you just take a point on your wire and then count how much charge passes through that point. dq is the charge passing through a wire, through a point on the wire in a time dt. So you just pick your point on the wire, count how many charges pass through your point, and in a given amount of time, the current is just the ratio. And the unit of current well, I usually denote it, it's usually denoted by these square brackets, is ampere. And 1 ampere is 1 coulombs per second. And circuits, ideally, they should always work the same way, but in reality, they don't. Okay, so, yes, questions?
Why don't we take the integral of the dq and dt?
Well, you see, this is not the derivative. It's not the derivative of anything. This is the definition. You just count the number of charges divided by how much time it takes. Of course, we will eventually define the charge. If you want to calculate the total charge passing through a point, then we can integrate. Sorry, the total charge dq by dt times dt. But in this present form, as I said, this is not the derivative of anything. That will be, in our later discussions, we will see that this will be equal to the derivative of certain other quantities, but here it's not really the derivative. Okay, so that is the current. And experimentally, it was observed that the potential created by the battery or the current is always proportional to the potential. You see, when we were discussing the potential, we always gave the analogy with the height. Well, exactly the same thing over here. So if you have let's say, if you have a rod filled with water, if you just tilt it very slightly, the water will flow slowly. If you tilt it more, the water will flow faster. So exactly the same. The analogy works also here. And usually we define that proportionality constant as 1 over R. R being the resistance. Every circuit has some resistance, small or large. And this resistance is actually a property of the circuit or property of whatever you are using with the battery. It doesn't change if you change, it's independent of I or V. Of course, this is just an idealization. Now, it turns out that this resistance of a material depends on the temperature. Well, why do they have the dependence on temperature? Well, just imagine this current is just the running of electrons through your wire. If you increase the temperature, the atoms in making your wire will be vibrating more violently. But if they are vibrating more violently, it's more likely that the atoms will just collide with the electrons and slow them down. So that is one of the reasons why we have temperature dependence. And in general, for any material, you can say that its resistance is given by 1 plus alpha t minus t0. Now, this R0 is the resistance of your system at a given characteristic temperature. So you pick up a temperature. At that temperature, you measure its resistance. Then at an arbitrary other temperature, T, it will have such a dependence. This alpha is some constant. Characteristic of your material. Now, one nice usage of this is that suppose you take some resistor whose resistance at the temperature T0 you know, then put it in some other place, and then measure its resistance once more. Well, if that resistance is different than your initial measurement, then you know that that system is at a different temperature. And by knowing, if you know the alpha for that material, if you measure the resistance of your resistor at that environment, then you can determine the temperature of that environment. So generally, how do you measure the temperature? Well, you use a thermometer, and which uses mercury is not forbidden. You cannot use mercury. You use alcohol, but alcohol just boils at some temperature around 100 degrees. You have the digital temperature. Well, digital temperatures have a different way of working, different working principle. They measure, as your friend pointed out, the infrared radiation. This is another means of measuring temperatures that can be that need not be in the range between 0 and 100 degrees Celsius. So if you want to measure the temperature of something that is 2,000 degrees, you just cannot use an alcohol thermometer.
Do we use thermocouple?
This is the thermocouple. Oh, no, sorry, this is not the thermocouple, but you can use a thermocouple also. The thermocouple is basically uses the potential created by applied temperature. Again, the idea is similar to this one, to the battery. Instead of the chemical solution, you use heat. If you just attach two different metals together And if you heat them, their properties, the change in the properties of these materials will depend on the temperature. And if you choose suitable metals, then that will create a potential difference, just applying a temperature. But this is another means of measuring the temperature. For example, this is something you can use in your electronic equipment. So just some part of the electronic equipment can have a circuit that will turn off your circuit if the resistance becomes larger than a given value. That will essentially turn your circuit off if your circuit is heated up above a certain limit. One application.
Like, does this mean that the resistors that you use in the lab like have different measurements in the summer compared to winter?
Yes.
That's the delta omega, right?
That is one factor in delta omega, one of the factors. You see, that delta omega is just the uncertainty in the resistance. So it can have very different reasons. One is the temperature fluctuations. Now let's see. We have the battery. We have our circuit. We have our load, let's say this is our load. What is the power? You can ask, what is the power delivered by the battery? What is the power consumed by your load? What was the definition of power? Work done in a given amount of time. Well, what does the battery do? It just carries charges from a lower potential to a higher potential. This is the positive, this is the negative terminal. So this is the lower potential, this is the higher potential. So the battery will just carry charges from one side to the other side. And let's say that if it carries a charge delta Q, how much work does the battery do? V times delta Q. So because when we define the potential, basically we said that V times Q is the change in the potential energy of the system as you move one of the charges Q from one point to the other point. That potential change is created by the work done by the external means. In this case, it is the battery. So if we move a total charge delta Q across a potential V, this is how much work we do. And this is done, if we want to calculate the power, this is done in a time delta T. So what is this? That's nothing but the current. So this is the power. And, well, this is valid whatever the system is. Now, if we have, well, this is called the Ohm's law. Not all the materials satisfy the Ohm's law, by the way. But in this course, at least, we will be interested only in the so-called ohmic materials. Well, we can say that V is equal to I times R, and hence P is equal to I squared times R, or I is equal to V over R. So P is equal to V squared over R. So basically, let's say if in a given system you know that the current is fixed, then this will be more useful for you. But if the potential is fixed, which will be the case in most of the practical cases, like when you are using a battery, you are basically fixing the potential. When you are using these plugs that provide electricity, you are fixing the potential. So in such case, if R is very small, then P is very large. P and also V, I, sorry. If you fix the potential difference, like if you are using a battery or if you are using any electronic device attached to this plug, you are fixing the V. So if R is very small, your battery is providing lots of power to your system. But what happens to that power? We know that energy should be conserved. Well, if the battery is providing lots of power to your system, it should be used by your load, whatever your device is. Well, most devices, they create heat, even if that is not what you really want, but eventually they create heat. Like, not these lamps nowadays, these are LED lamps, but before we had these warm light lamps, which were working mainly by heating a metal filament. So you have a metal wire which can resist very high temperatures. It doesn't melt at high temperatures, but if it is heated to very high temperatures, it starts glowing. So that is how we created electricity, sorry, how we created light. Nowadays we have these LED lamps. Their working principle is, well, quite different. But in any case, you provide power. Most of it will be converted into heat. There is nothing much you can do about that. But heat will melt your equipment. So what you want is, well, you see, if you look at over here, since we are fixing V, this is a problem for low resistance. If the resistance is very low, it attracts so much current, it pulls in so much current that even though the resistance is low, it creates a huge amount of heat. And hence, it can melt and it will heat up, it will melt, and it can create fire. So that is why we have fuses. Well, there are various types of fuses. One type, for example, they look like very small cylinders. Inside, you have a wire. These are the electrodes. And inside, there is a thin wire. If the current in that thin wire becomes too high, it breaks. So this is basically the kind of fuse also the cars have. Have you seen the fuses of a car? How many of you are driving? And you weren't curious to open the fuses? Well, most of the, well, at least the ones that I know, they are basically, they have such a plastic part and they have two electrodes. They have more or less like this shape. Here there is a very thin wire. If the current goes above a critical value, it's usually written on the fuse itself. So if it just goes above that critical value, the wire just burns down. And since when the wire burns, there is no current flowing anymore. The current just cannot flow. It stops the current. Nowadays, of course, at homes and, well, I think here, no, probably outside, we have other types of fuses. In this case, since the wire has melted, you cannot use the fuse anymore. You have to throw it away. But nowadays, we have other devices where, okay, let me try to sketch it. Let's say this is a box. Here there is a switch. Now, if there is too much current running in your system, the switch just goes off. And the working principle is mainly, here you have a lever. There is a compressed spring. No, it's not uniform. Here there is a compressed spring. Here you have some metal. It's made up of two layers, two different materials. So you send current through this wire and get the current out of this wire. So the current comes here and then leaves here. Everything is working fine. But as the current is running through your fuse, it heats up. And if the current is high enough, this will bend such that it comes over here. But at this point, your circuit is now open. So if this bends, then there's no current running through your system anymore. And well, there's another mechanism that blocks this, so this spring just pulls it down. Well, okay, I didn't manage to draw it good enough, but this is basically the idea. So the circuit, this is a typical circuit breaker. This lever just goes down. Now, so probably it's not over there. The current is taken somewhere from here. This is the current. So let's say there is a connection over there. So when it comes here, this just pushes this lever down, and your circuit is now open. There's no current flowing in your system. The nice thing about this thing is, since nothing breaks down, you can just turn it off. Turn it by just, this goes down, and then if you lift it up, it continues working. But of course, you should better make sure that you first discover what was causing this huge current, and when you fix it, it keeps on working fine. This kind of saves us from burning our house down, let's say. Any questions? Now, one reason why that happens is, at least here, you see there are many plugs in this house. Usually what happens is the electrical inlet into a house and the outlet from the house is just one. There's just these two wires coming in our houses. So every plug will be attached to these ones. So here we have one circuit. Here we have another plug, which we can attach another circuit and another plug, etc. So each one of these circuits will draw their own current. Let's say this will draw a current I1, this will draw a current I2, this will draw a current I3. If it happens that one of those devices attracts, let's say, too much current, then your fuse will just prevent any current running in your system. And one of the reasons why any given device can attract too much current is what we call a short or a short circuit. Now, it is essentially when, let's say, you have, this is your circuit, whatever resistance it has, but some reason, some wires, they just touch each other. In a sense, bypassing this resistance. Well, if you bypass that resistance, well, now there's no resistance in my circuit. R becomes very small. If R becomes very small, then the current will just go to infinity almost. The current will be huge. The power delivered to the system will be huge. And, well, it will start burning. Something will start burning. Now, these shorts usually happen, for example, if you look at this wire. It's quite thin. Some part of it will bring the current into my computer. Some of it will just take it away from my computer. But if I step on this, I can just break the insulation between those two wires. And rather than going through my computer, the current will just go through that short, causing the fuse to go off. Now, another thing when you are dealing with circuits is just make sure that you know the classifications of your wires. Well, there was a nice example in your book. You see, when you buy some wires, they will have their classifications, like how much current they can carry at most. So let's say you have a heater. Of 1,800 watts attached to, let's say in Turkey we have 220 volts. Well, this is the power it consumes. Now the first question, what's the current it uses? How much current does it draw from their circuit? Well, we said that the power was the voltage. Remember, voltage is in a sense, the work done per unit charge. So how much charge passes through our system per second? Well, that is the current. The power is the voltage multiplied by the current. Now, we know the power. This is 1,800 watts. This should be equal to 220 volts multiplied by the current. Or the current is 1,800 watts divided by 220 volts, which is, some of you have a calculator, or let's say around 9 amperes. So if your wire is classified as able to carry at most, let's say 8 amperes, then you shouldn't be using that wire. In fact, if you have a notebook, for example, the laptop doesn't use much power. The wires are usually thin. But if you have a heater, the wires carrying current to the heater would be much thicker. They will be much thicker so that they can carry more current through their system. Any questions? Okay, so let's go back to resistance. You see, most of the resistors or the wires we have, they are essentially very long cylinders. They have a cross-sectional area A, they have a length L. And again, you can just ask, how does the resistance of a wire changes if you change its length or if you change the cross-section? And experimentally, it is observed that the resistance is directly proportional to its length. If you have a longer resistor, then it will have a larger resistance, and inversely proportional to the area. So even though if you have two resistors made up of the same material and they are of the same length, if you change the cross-sectional area, if you double the cross-sectional area, the resistance will be reduced by a factor of 2. You can just think of this as, well, in a way, just number of lanes in a highway. If there are more lanes, that is, the highway is larger, in this case, the analogy will be the area is larger, you can have more cars moving at a given time. So in this case, it will be the electrons. There will be more electrons moving in a given time. So the current will increase, which means the resistance has dropped. And there is this proportionality constant. This is called resistivity. Now, this is a property of the material used. In fact, the temperature dependence of the resistance is due to the temperature dependence of the resistivity of the material. So rho changes as a function of time. Well, sometimes we also need the inverse resistivity, which we call the sigma. Well, if the resistivity is low, it means it's a good conductor. So this sigma will be large. So large sigma means it's a good conductor. So that's why it's probably called the conductivity. Large rho means it's resisting the current. Large sigma means it's a better conductor. Any questions? So we will continue on Thursday.